To make this transition, when can this guy do it? If I gave it a frequency that is slightly lower, right? I don't give it new, but I give a slightly lower frequency, then what happens? That slightly lower frequency, as the molecule is moving towards it, it will actually think it is higher, and if it is correctly calculated and correctly given, what would happen? This small shift, the Doppler effect, would actually take that frequency and move it into resonance with this two state, and therefore the molecules moving in this direction are actually asking for a frequency that is slightly smaller than what this difference in state actually asks for. Let me assume that this is 25,000 wave numbers. I give 25,000 wave numbers. Who makes the transition? The stationary guys. The guys moving towards it, they think it is 25,100. Can't make the transition. The one moving away from it, they think it is 24,990. They can't move either. But if I give 24,990, what would happen to the molecules moving towards it? That 24,990 would actually become 25,000. Oh, then they are happy they make the transition. In other words, you will find that to make this transition, different molecules are asking for different frequencies. And therefore, the transition occurs not just at 25,000, the transition occurs below and above also. Because there are some molecules who are asking for a lower frequency, there are some molecules who are asking for a higher frequency. And therefore, you will find this curve naturally looks like. But why are molecules moving in the first place? Because we know from Maxwellian speed distribution that at any given temperature the molecules have a distribution of speeds and a distribution of velocities. Which means there are molecules moving this way, molecules moving this way, and what is their distribution, speed distribution determined by? Temperature. Higher the temperature, what happens to the distribution? It gets wide. And therefore you will find that at room temperature molecules are actually moving with different speeds. And that speed distribution is essentially the reason as to why molecules are making transitions from one state to the other, not at one frequency, but at different frequencies, depending on what their speeds are. Zero speed, they take the frequency required to make the transition. If they have a speed towards the source, velocity towards the source, they need a slightly lower frequency so that it can get shifted into resonance. If they are moving away, they need a frequency that is somewhat higher so that it can get shifted into resonance. In other words, because we have a distribution of speeds, this line is still going to be sharp, this line is actually going to be somewhat broad. What do you think will happen if I increase the temperature of the system? It's going to get broader. And what do you think will happen if you get to low temperatures? Sharpness. That's the reason why in our experiment we go to 10 Kelvin and do all our experiments. Because if I go to 10 Kelvin and do all my experiments, the speed distribution is almost non-existent, and therefore the width that I get because of Doppler is completely killed, and my peak just becomes sharp. I want sharpness. We want sharp peaks. And if you want sharp peaks, you have to know first why the peaks are broadened in the first place. One of the main reasons as to why peaks broaden is because of such mechanisms. We saw two of them. One of them is natural broadening, and the other one is Doppler broadening. Doppler broadening has to do with movement of molecules in space. What has natural broadening got to do with? Lifetime. That's where the dynamics comes. One of them is evolving in time. You put it up there as a matter of time, it just decays. There are dynamics to that process. The other one is the dynamics associated with the molecular motion in space. So Doppler essentially comes under that category. The actual line that you will see, mind you, is a combination of both. Because both are occurring. You have natural broadening and you have Doppler broadening. So what you really see there is actually a combination of these two. Don't worry at this point in time as to how I can separate them out. There are mathematical tools called deconvolution which will help you to do that. It's not necessary to do that at this point in time. At this point in time, all I need to know is that there are these two different methods or two different reasons as to why lines are not sharp. The lines are actually broad. So when you took your UV visible spectrum, when you did your fluorescence spectrum, when you did your infrared spectrum, you never got sharp lines, you got broad lines. The reason why you got broad lines was because all these factors and many others were actually operating, causing those lines to be broad, and basically telling us all the time that there is a certain dynamics that's going on in the system. So of course, when we do the experiments, we need to do the experiments and we sharpen the speed. What are we doing? We're completely freezing them out. And therefore there is no speed distribution. But in the process we are killing the dynamics. We have lost that information. But our policy is who cares? We don't want that. We want sharp lines because we need to look at sharp lines to do something else. But if you are a person who wants to understand the dynamics of what's going on in the system, you will actually look at the width. You already know how to get the temperature of a system, right? Most probable J, you remember? We just got the most probable J, and from the most probable J we got the temperature. That's one way of doing it spectroscopically. What's the other way of doing it spectroscopically? Just go and find out the width of the line. And the width of the line must be in some ways related to the temperature. Higher temperature, it must be broad. Lower the temperature, it must be sharp. And therefore, with that, you must be able to find out what the temperature of the system is. If you took your Doppler equations from physics, if you took your Maxwellian speed distribution, put the two together, you will actually be able to derive this. You won't derive this, I just give you the equation. It's not too difficult to derive if you want to. See this. When I say delta UD, I am talking about the width due to Doppler. Because there is also a width due to natural broadening. And what is delta UN equal to? We just saw that. Yeah, I will give you this today. You can actually derive for the delta mu Doppler, as I said, by taking the equation, the Doppler equation from physics, and taking, you have that 1 over minus v over c into mu naught, you get that equation. You take that, plug it into your Maxwellian speed distribution, and you'll be able to find out what the width of it must be, which is the Doppler width. And you will actually see that equal to 7.1. This is the molecular weight. It's not the actual mass of the molecule, it's the molecular weight. So the carbon dioxide, it must be 44. Benzene, 78. That number comes in here. This is the temperature of the system. And this is the frequency at which you are irradiating the molecules to make the transition. So this is the equation which you can actually derive by taking the Doppler equation and plugging that into your Maxwellian speed distribution. And if you do a little number crunching and solving out those equations, this is what you will get. What you really need to do is to look at this equation and try to understand the operative parts of the equation. That's the way you look at equations. Every little term in the equation is actually trying to tell you something and see what it is telling you. The first part is a constant, don't worry about it. So it's scaling it. And you don't have to worry anything more than that. What is this? The frequency at which the transitions are being made. This temperature. But we knew all along, if I increase the temperature, this must go up. We suspected that, except now we know it's not a linear relationship, it's a square root relationship. It goes as the square root of the temperature. And what's this? Molecule. So heavier molecules, M is large, delta U is small. They are more sluggish. And therefore you will find that they don't really contribute to a whole result of it. But lighter molecules will actually increase the Doppler width. So all you need to know is to keep in mind, if you are dealing with very heavy molecules at low temperatures and low frequencies, you really don't have to worry much about Doppler. We do infrared spectroscopy. And let's say somebody else does, Arun came the other day and he's doing microwave spectroscopy. And there are other people who do UV visible spectroscopy, electronic spectroscopy. So while Arun does rotations, we do vibrations, and somebody else does electronic, we are 3 people looking at 3 different regions of the electromagnetic spectrum. One is in the microwave region, one is in the infrared, and one is in the UV vis. Who do you think will suffer the most with regard to Doppler? It's a great proportionality on omega. Therefore, the UV vis people whose frequencies are much larger, they are like 25,000-30,000 wave numbers, they will have the largest Doppler width to contend with. Next comes infrared wave, few thousands of wave numbers. Go to microwave, it's a few wave numbers. So as this omega gets smaller and smaller, this gets smaller and smaller. So this equation is actually trying to tell you that if you are a UV vis spectroscopist, electronic spectroscopist, watch out. Doppler width is going to be after you. If you're an infrared spectroscopist, well, it will be there, but no big deal. If you're a microwave spectroscopist, you probably shouldn't even worry about it. Because omega being so small, that their NOD will be actually extremely small. Later we will learn when we do NMR spectroscopy, we are really looking at radio frequency, and that's even smaller. And that's the reason why you will see, I don't know if you have really looked at an NMR spectra. So have you? And what's the first thing that struck you that you didn't see anywhere else? Sharp peaks. Why sharp peaks? Doppler is not contributing. What about natural? It won't contribute there either, because NMR is this far away, energy levels. Microwave is this far away. Infrared is this far away. The energy levels are getting larger. And of course, for UV vis, I have to go taller. Make it that way. The point is, and higher you go, the molecule has a greater tendency to jump back quickly, because you are really tilted it far away from equilibrium. Which therefore means that in the UV vis, your lifetimes are likely to be very, very short. If the lifetimes are very short, what happens to your width? Oh, they get broad. Come to infrared. I'm only a few thousand wave numbers away. Not so bad. The lifetimes are typically milliseconds. UV vis lifetimes are typically micro to nano. Short. Microwave, even short, even longer. You know, they are order of few hundreds of milliseconds. Go to radio frequency, NMR region, the decay is extremely slow. And therefore you will find that natural broadening is very small in NMR. Doppler broadening is very small in NMR. Why is Doppler broadening small? Because this fellow is small. And therefore NMR suffers the least of the broadening issues. And that's the reason why in NMR you got all these peaks which are extremely sharp. But you go to infrared and rotations and particularly UV vis, you will find that lines are as fat as you can possibly see them. Even in NMR, if it's a solution, that's fine. But you put the same molecule in a solid and try to do NMR, the peaks are this big. Why? In a solid, when you excite them, they are interacting with all these things around. Because in the solid, molecules tend to be closer to each other, they are interacting. When they interact, the lifetime tends to be short. Because they interact, I give energy away and they jump back. In other words, if I have been alone out in the open, my lifetime is much longer. But if I'm interacting with a lot of people, my lifetime tends to get short. That's what happens in solid state NMR. All solid state NMR spectra are this wide. Why? Because you have made the lifetime extremely small in that situation. You can therefore see that the line widths are actually trying to tell you about the dynamics of the process going on with regard to that molecule. We have just looked at two. Doppler and natural. There are many others. There's collision, there's pressure broadening, there is lifetime, time of flight broadening. There are so many others. We will not get into all of those at this point in time. But at this point in time, all I'm trying to do is to introduce you to the concept that lines will not be sharp. I just want you to realize that lines will not be sharp. They will have a width. And they have a width because of various dynamical processes. And all we have done is we have seen two of them. Natural broadening, which actually stems from the Heisenberg principle of uncertainty, and Doppler broadening, which stems from the fact that molecules are actually moving back and forth with respect to each other, which causes the Doppler shift in their absorption. And the collection of all these shifts is what gives me that width, and this is basically what we are looking at. So I think I'll stop here, because I need to go and get something straightened out. But I'll need to make a few announcements. We didn't have a lecture yesterday the Curie Club because the NK network gave up